Welcome to our third lecture of RF and millimeter wave IC design in Unit 2. And in today's class, we'll start with image reject receivers. So far we have looked at a simple heterodyne receiver and an extended version of double down conversion receiver. And there are other receivers too that we will see after this image reject called as direct conversion receivers. The basic idea in an image reject receiver, so in the regular heterodyne receiver, what we were doing is we were trying to employ filters to filter the image, and we saw the trade-off between image rejection and channel selection. But now in the case of image reject receivers, the idea here is not to directly filter out the images. Instead of filtering, we use a method of suppressing the image or cancelling out the images, right? So thereby the whole idea of image reject receiver is basically to come out of the trade-off between the image rejection and channel selection. That is the idea behind this image reject receiver. So we'll start with this image reject receivers now. But before discussing the architecture of an image reject receiver, we may need to understand some fundamentals. Probably you'll be knowing this through your communication system courses, but we'll just review that in order to understand more about image reject receiver. So here the idea is to suppress images without filtering, without using filters. Now, then how will you suppress image? That is what we will discuss now. And the main intention is to avoid the trade-off between image rejection and channel selection. Right. So, as I mentioned before starting the architecture, let us see some of the basic things. Let us start with how to perform this 90-degree phase shift operation. How to perform a 90-degree phase shift operation. We'll see mathematically first, and then later we will see how to implement this on implement using a circuit, and later conceptually also we will see that. All right, so say if I have a signal with an amplitude A at a frequency of omega c, like A cos omega ct, I can represent this in another form, like A into e to the power of the phasor e to the power of j omega ct plus e to the power of minus j omega ct by 2. All right, this is how I can represent this cosine wave. Now we know that if we apply 90-degree phase shift to a cosine wave, we will get sine wave. But how will we get that? Now let me do that mathematics here. So yeah, so if I apply 90-degree phase shift, what I want is A cos of omega ct with a phase shift of 90-degree. So that can be further written as A by 2. Here omega ct term is shifted by 90 degree plus e to the power of minus j omega ct also with 90 degree. This is how we can uh, write that. Further, I can simplify this as e to the power of j into minus 90 is nothing but minus j into e to the power of j omega ct plus e to the power of j90, it is same as j into e to the power of minus j omega ct. I hope you guys are following this. Or if I separate even the amplitude, uh, yeah, in this form I can write. or this is so what is this, what I have written? This is equal to, if I write in this form, a into minus j omega ct plus, yeah, so whatever I have written now is equivalent to sine wave, right? So that can be written as a sine omega ct. And this is clear, we know if you apply 90-degree phase shift to a cosine wave, you will get a sine wave. So if I see this, see the spectrum here. So what I have is a sine wave, sorry, a cosine wave. Cosine wave I can represent using two impulses, one at omega c and another at minus omega c, depending on the progression, how the wave is progressing, and both with amplitudes of a by 2 here. This is your cosine wave. Now, if this cosine wave, if I'm applying 90-degree phase shift, what I'm getting here is, by looking at the components what I have written, I can say that at minus omega c, you can see that minus omega c, you have a component of j into a by 2. So minus omega c, what I have is a component which is j into a by 2, and at plus omega c, the component is minus j into a by 2. Right. Again, this is not something new. This you already know this. Right. Now, so what we will do here is so by looking at the cosine and sine wave component, we can see that, or we realize that the amplitudes have both real and imaginary component, right? So for cosine wave, it is purely real, a by 2, a by 2, and for sine wave, there is an imaginary component which is j a by 2 and minus j a by 2. So just I am translating this into a plane where I can mark the real imaginary components versus frequency. So if I do that, are you guys with me? So what we are doing is just a 90-degree phase shift operation, and we are going to do some we'll have some takeaway from this. Are you guys with me? Can I get some response in the chat box? All right. Uh, okay. So what I'll do now is, this is the omega axis. So why we are doing this in very detail is, understanding this and practicing this will help us to deal with image reject receivers in a better form. And all right, so what I'll do now is I am just going to express the real components in this axis and imaginary components in this axis across omega. Right. So I'll start with this. Initially, what I have is, I have a cosine wave, say cosine wave at omega c and minus omega c. Their amplitudes are real. So I have real amplitudes of a by 2, and here also I have real amplitude which is of a by 2. Now what happened to this cosine wave when I apply 90-degree phase shift operation? I saw that when I apply 90-degree phase shift operation, this a by 2 has translated to minus j a by 2, and this a by 2 at minus omega c is translated to j into a by 2. That means the component which is now available at omega c got shifted clockwise, and the new component is having an amplitude of, so this was the shifting happen, and now this new component is having minus ja by 2. Similarly, the component at minus omega c, which is a by 2, which is shifted and anti-clockwise, and the new component is j into a by 2. All right, I hope this is clear. So this is what happened when you started with a cosine wave. you apply 90-degree phase shift. So the real component at omega c shifted clockwise, and the real component at minus omega c shifted anti-clockwise, right? Now in a similar way, if you apply, or if you try to do 90-degree phase shift operation on a sine wave, uh, so this is, say this is sine wave. Now if you try to do 90-degree phase shift operation, what you will get is, you have sine omega ct. After 90-degree phase shift, we will get minus cos omega ct. All right. So let me see the components for that. So I'm starting with the sine wave 0. It is having at omega c, it's having minus ja by 2, and at minus omega c, it is having ja by 2, right? Now so I know the result. So when a sine wave, when it is translated, or when a sine wave, when I apply a 90-degree phase shift operation, what you will get is minus cosine wave. So if I write the resultant spectrum of minus cosine wave at omega c and at minus omega c, you will have this one. This will be 1 by 2, and this will be a by 2, and this will be a by 2. All right. So now now let's assume that a is 1. So this amplitude is, say, j by 2, and this is minus j by 2, and this is 1 by 2, and this is 1 by 2. So what I'm looking at here is, if you look at the sine wave and the 90-degree phase shift operation, how this 90-degree phase shift operation can be represented. So how can I say, or what function, what is happening to the sine wave when a 90-degree phase shift operation is applied to the sine wave? Can you tell me what operation is happening here? Or the shift by 90 degree can be otherwise called as what? Have you come across something like this in your communication systems classes? Can I get your response in the chat box? Yes, Pratap. I hope you missed the H. Yes, Hilbert transform. So this shift by 90-degree operation is otherwise called as Hilbert transform. So how do you apply Hilbert transform? Uh, it is by multiplying a signal with a function, signum function, but not directly with signum function, but by multiplying with minus j signum function, right? Yes, it is very much similar to Hilbert transform. Yes, we know that is right. So, how, I hope you know what is signum function, right? Signum function, if you represent, it is basically something like this, with plus 1 and minus 1. Now, what we will do here is, in order to get 90-degree phase shift operation, we do this minus j signum of omega. So, if I do that, the function what I need to multiply here is nothing but at plus j, and this is at minus j. So when I do this, I'll get minus cosine wave. So when a 90-degree phase shift is applied, it is basically, it is equal to doing a Hilbert transform. So if the transform of x of t is x of omega, if I want to apply 90-degree phase shift, then that is equal to minus j signum function into x of omega. That will give you the 90-degree phase shift operation. All right. So shift by 90-degree is Hilbert transform. Now we are interested to know the same thing in a modulated signal. So let us just try a modulated signal. The idea remains the same. Say we have a modulated signal, and if I am representing that modulated signal as x of t equals a cos omega ct plus the phase shift associated with it. Then the 90-degree phase shift operation will definitely give you a sine wave with the corresponding phase. All right. So why did I mention about modulated signal here is we'll usually represent a modulated signal with this. All right. So now if I try to represent this on this with imaginary and the real terms, how we will draw is, so this is your omega axis, this is real axis, and this is imaginary axis. So initially at omega c and minus omega c, you'll have components like this. Now after 90-degree phase shift operation, this will be shifted towards this side with 90-degree clockwise direction, and here you will have anti-clockwise movement. All right. So this is just to represent modulated signal over there. All right. So one more thing is, so if I have a signal, say x of omega, now we know that Hilbert transform is nothing but 90-degree phase shift operation. So what will be the result if I am actually applying this signal to a cascade of Hilbert transform? So signal is there. If I am applying that signal to a cascade of two Hilbert transforms, what will be the resultant? Any idea? Can I get your response here in the chat box? Yes, 180 degree. Yeah, that is same as negation of your signal x minus x of omega, right? So cascade of two 90-degree phase shift operations negates the signal. All right. Now, let me give one question to you. So plot the spectrum of a signal a cos omega ct plus ja sin omega ct. So when I'm asking you to plot the spectrum, what I'm expecting is on the same use a spectrum or plot the spectrum on the plane which you can mark both real, imaginary, and uh, real and imaginary components across frequency. So please perform the operation and just tell me what will be the final. Yeah, you can do that even like looking at the question itself. But if you can perform the operation on the axis on the real imaginary frequency plot, just tell me what will be your final answer. Any response for this? Any answers? What will be the resultant if you have this is omega, this is imaginary, and this is real? All right, let me just I'll use real components with this color and imaginary with this. So A cos omega ct is your, you can perform the operation. I'm just doing it for you. At omega c and minus omega c, A by 2, this is A by 2. It is a cosine component. Now sine component, I'll use another color, which is here at minus j A by 2 and j A by 2. So what you can see now, yes, you will, the final result will be, you will get a component with an amplitude of A at omega c. So what I have done here is, I've taken, so I know that the cosine wave will have real components at omega c and minus omega c, which is A by 2 and A by 2, that I marked first. Then you'll be wondering why I'm doing this in very like in detail, because this understanding or this experience is very much essential, or help, this will be helpful when you start, when you do with the image reject receivers. Now the sine components, and just this A sine omega ct can be represented by minus j A by 2 and j A by 2 at omega c and minus omega c. Now the only operation I need to perform is, I need to multiply the sine components with a j. So that multiplication I'm doing using this red color. So when I do, when I multiply with j to this, when I multiply this with j, it will become A by 2. So I'll add, because j and j minus, so this will become A by 2. So I'll get one more component here, which is A by 2. I need to add that because both are appearing at the same frequency. Yeah, you'll get one more component at A by 2. And when you do the same thing on the other side, when you multiply this with j, you will get minus A by 2. So that component will be here. Right. So at minus omega c, those components will get cancel each other, and at the omega c, that components will get added up, and your resultant will be, your result will be, at omega c you will have a real component which is of value a. Okay, so at omega c you will have, you will be adding those two amplitudes to get a value of a. All right. Now, let us see one way how to implement a 90-degree phase shift operation using some components in a practical way. So, how if you have a signal, you want to implement a 90-degree phase shift between those two. So, how will you go about that? There are different methods. There are different methods to implement it. We will see one typical method, and we'll focus our attention to deal the same thing with the image reject receiver. So how to implement a 90-degree phase shift operation. Any idea? Can I get some response? Say using passive components, how will you implement 90-degree phase shift operation? Yes, LC ladder is one option. Yes, that is there. Yeah, lambda by 2 transmission lines. All right. Um, with passive components, yeah, using RC also we can do the same thing. So that is the very basic form. So we'll see how it can be implemented using an RC. So let me take two RC networks. All right, so just I'm marking this as C1 R1 and this as R1 C1. Definitely there will be mismatches, but for the time being I'm not considering that. And this is V out 1 and V out 2. If I configure two RCs in this fashion, definitely V out 1 and V out 2 will have a 90-degree phase shift. So how to see that? So in order to understand that, you can just write the transfer function from V out 1 to V in and V out 2 to V in, and you will see that there will be a difference between a 90-degree phase shift between those 2 points, V out 1 and V out 2. Can you guys try and let me know, are you getting the 90-degree phase shift operation between the 90-degree difference between these two? So what is your upper arm? You have a capacitor and a resistor, and the if you write the transfer function of this, so this transfer function looks like what? Can I get your response in the chat box? Yes, that is a high pass. So this is a high pass transfer function. So I can write this as V out 1 by V in can be written as uh, yeah, S into R1 C1. I'm just writing the final expression 1 plus S R1 C1. So that is for your high pass function. Similarly, the lower arm is a low pass transfer function. So if I write that low pass filter, this is V out 2 by V in is equal to 1 by 1 plus S R1 C1. All right. So we want to know what is the phase shift between these two arms. So let me write the angle of this function. The numerator is 90 and denominator is minus tan inverse omega R1 C1 is angle of the first arm, the upper arm. And for the lower arm, you write it is minus of tan inverse omega R1 C1. So now if I take the difference between these two low pass filter, you will get 90-degree and yeah, 90-degree or pi by 2, both are same for all frequencies. Right. So this is one simple way to perform this 90-degree phase shift using passive components, RC components. And one more thing you can see here, the output V out 2. So since there is an 90-degree phase shift, I can say V out 2 is the Hilbert transform of V out 1. Is the Hilbert transform of V out 1. All right. So why we have discussed all these things starting from an 90-degree phase shift operation is, as I mentioned, this is for to study image reject receivers. So that image reject receiver study we will start from our next class, because it will take little time to complete the calculations of image reject receiver. So we will start from next class onwards. So for today I am winding up here. Thank you so much for joining. If you have any questions, you can ask.